Hello and welcome everyone to our new episode of Wissenschaft fürs Wohnzimmer, Science in the Living Room. We have an English episode today, and I'm very happy to have Paul Myers with us from University of Alberta. My name is Stefan Jurike. I'm a climate scientist and oceanographer, actually not any longer at the Alfred Wegener Institute, but at the Geomar Helmholtz Center for Ocean Research in Kiel. And I'm gonna be one of the hosts for today, but I don't want to keep you waiting too long for our interesting and exciting talk today, so I will just hand over to our other members of the hosting team.
Yes, hello and welcome also from my side. I'm Melanie Habermann. I'm a PhD student at the Helmholtz Institute for Functional Marine Biodiversity, and I'm working in the Biodiversity Theory group as a mathematical modeler. If you want to hear more from us, you can always follow, leave us a like also if you like the stream and the talk today, and click the bell to get the reminder whenever we upload a new episode.
Hello, everyone. I'm Denise Vural. I'm also a PhD student based in Berlin, but from Potsdam, Abi Potsdam, and focusing on permafrost coasts. And today we have a very exciting speaker. So without further ado, I'm going to briefly introduce him. So we are excited to, let's do it like this. Awesome. We are excited to welcome Professor Paul Myers, a leading physical oceanographer from University of Alberta, Canada, to episode 176 of Science for Living Room. Professor Myers is internationally recognized for his work on ocean circulation, climate modeling, and the role of freshwater in polar systems, particularly in the Arctic and subarctic regions. With his expertise in high-resolution computer models, he brings critical insights into how warming, melting, and ocean dynamics are reshaping the Northern Hemisphere's climate systems. Today, he will help us explore the science behind Arctic freshwater flows, ocean stratification, and whether the Day After Tomorrow movie might have gotten a few things right. So over to you, Paul.
Thank you. Let me just share my screen, bring up the slides, and oops, wrong button, and also hide the controls so we can see that. So good evening, or I guess I should say guten Abend, although after that I'm going to have to go back to English. My German is not of a level to give a scientific presentation. So thank you very much for inviting me to come to this event and present on some of the science I'm interested in. I think it's the initiatives like this that reach out to people and to discuss science and allow people to see what's involved in scientific research and learn about it is fantastic. So tonight I'm going to talk a bit about the ocean and its links with the Greenland ice sheet, how the ocean plays a role in the enhanced melting of the ice sheet, and then when that fresh water melts and enters the ocean, what are its impacts? And because I guess it's topical and controversial, how does this melt lead to the sort of the idea of a day after tomorrow? What does that mean? Questions like that. So that's what I'm going to be talking about in this presentation. Now, a bit of a background. I was asked to talk about, why am I interested in this? How do people get into careers in science and working in this? So who am I? Why am I a physical oceanographer and an ocean modeler? As Denise mentioned, I do ocean modeling. So in one sense, I've always been interested in the ocean. I come from a background of a family of fishermen. My grandfather and his father before them were all fishermen out of the United Kingdom, Hull on the East Coast. And they fished all over these regions that I'm going to be talking about. So I grew up hearing sea stories about the Nordic Seas, Reykjanes Ridge, Cape Farewell, the Labrador Sea. The picture above was actually my grandfather's last trawler he fished from in the 1950s to 60s. So yeah, background of sea. And related to that, I've always loved sea stories and, tales of ocean and Arctic explorers. I grew up reading about all the explorers, the search for the Northwest Passage, Nansen and his drift of the Fram in the Arctic, Antarctic and other sea explorers, Captain Cook and everything. So many years I've been, following sea activities. I guess, when I visited Bremerhaven, one of my highlights was visiting the German ship museum there, seeing the remains of the Hanseatic cog they've recovered, as well as going on the reconstructed one. So these are all things that are of interest. And then this interest goes, from the stories to the history to the music. I'm someone who likes folk music, and I always liked songs of the sea. And I thought that just as, again, because I want to talk about this waters going on Greenland into the Northwest, I thought I'm going to start with, assuming the click opens.
For just one time, I would take the Northwest Passage to find the hand of Franklin reaching for the Beaufort Sea, tracing one warm line through a land so wide and savage, and make a Northwest Passage to the sea.
So as I said, I just thought I'd put that on, again, background and why I'm so interested in that. That said, I love the ocean. I love everything as it has been said, but I'm absolutely not handy. I do not, if you put me in a chemistry lab, I will break everything. I have no practical sense. So the way I go to the ocean is, I was very happy when I learned it's based on mathematical theory. Equations that describe how fluids work. You can build computer models that divide it into grids and solve it. And that was my path into the field that just allowed me to explore it. I did first an undergraduate degree in math. Then I did my master's and PhD in aspects of ocean modeling, ocean physics, taking those applications, seeing how they work, seeing how the ocean revolves in the climate system. Traveled around, spent some time in Europe, back to Canada. I've been where I am now in Alberta for over 20 years. Although I've had a lot of links with Germany. I did an extended research visit in Geomar and Kiel in Germany on ocean model development. And then I was involved in over 10 years in a Canada-Germany joint training program linked with the University of Bremen and Avi, where we had students from Canada go over to Germany. German students come over to where I'm working in Alberta to, again, build, share models, look at different applications, all related to high latitude climate aspects, including the Arctic and everything else. So again, that's a bit of background of how I've got into doing what I'm doing. And in terms of what I'm doing, again, Denise in the introduction mentioned something about high resolution modeling. And, there's many ways one can model aspects of the system. As I said, I'm interested in models because there's math, and models are built around three components. There's mathematical equations that describe how the physics work. Don't worry, I'm not going to come back. I'm not going to do any math and details. We need to know conditions about the actual ocean. So what is it like in this plot around Antarctica? Its temperature, its salinity, the velocity, structures of the ocean to get the model going. And then boundary conditions, how the water's forced. You need to know aspects about the tidal forcing. You need to know winds like this plot here that blows the ocean current. We need to know the surface heat, the incoming radiation, the air-sea exchange. And especially for the highlighted oceans, we need to understand aspects of fresh water, river runoff. As oceans warm, as land warms, we get melting, say, permafrost that change river runoff into the ocean. And then especially ice sheets. How does the melt from the Greenland ice sheet get into the ocean? How does it affect its physics? How do we put it into the model? How do we have glaciers, icebergs, all of that? How does that play a role? And that's things I've been looking at. And one key element I want to mention, the real world is sort of what we consider as continuous. The ocean flows everywhere, the atmosphere is, or if you just think of your bathtub, you've got the water on, water's continuously flowing in from the tap. But to solve it computationally, we have to break it into pieces, some sort of discrete pieces. So we take some system and divide it into boxes that will then solve our equations on. It's just like our tap, having the water falling through in drops, and we're modeling each piece and then putting it together. And that's an important thing to think about when we do computer models is for the climate, we have all these boxes, the pieces that exchange the current, the heat, the atmosphere, the fresh water, the salinity, soil, vegetation, carbon dioxide, etc. All sorts of pieces. But with those models being computer models, we have to put them into computers. And computers, even with all the power today, still have finite resources. And you have to decide where you want to put your resources. And this, depending on the questions you want to answer, you go in different ways. Sort of with this triangle I really like that comes out of an IPCC climate report. You can have complexity. You can have more and more parts of the climate system. It's important. So you can look at how the vegetation links with the ice, the biogeochemical aspects, etc. You can run lots of simulations and then average them to like get weather forecasts, your probability of precipitation. Or you can put lots upon lots of grid cells to really represent the small scale physical processes in the ocean, the atmosphere, and the climate system to then look at what is their integrated impact. And you really need people doing all of these aspects. They're all important. I'm going to focus on resolution just because I'm really interested in those small scale physics, but I'm not saying the other aspects are not important, but what I'm going to talk about is based upon what I'm really interested in, what I want to really look at it. And for example, of oceans, ocean currents, as we change the resolution, this is just sort of the Gulf Stream. You can get from very basic from models to start getting more details, more detailed patterns. You can still have the warm water being transported, but there's meanders, small scale separated features, eddies that are very important for the ecosystems, the biology, all of which change at least some aspects of our understanding. And then you can link that to satellite pictures that have the truth. So these are things I want to look at. And I've been very interested in building higher and higher resolution models. So for as an example, this is from some of the stuff we've been doing where we've built models that represent the entire Arctic Ocean and parts of the North Atlantic with those boxes of sizes of less than 1 kilometer. And just so you know, this white here is not the boundary of the model. It's just the area I've made this movie from because the files are huge and there's a lot of expense. But the key thing as you go to these high resolution models, you can see the flows, you can see the currents. The one on the right is just a blow up of part of the Arctic, but you also see all these small scale meandering circular features. They go back and forth between the seasons, depending on where the sea ice, there's damping, etc. But they play a big role in mixing in the ocean, transporting properties, say, from the coasts, where we have runoff and melt from rivers, or when I get to Greenland, the ice sheet, into the interior. And then what is the integrated effect of these small scale features and how important are they in representing behavior is one of the things I'm looking at and why I want to touch on these questions. And this is important because if you look at textbooks, you go to a class or a web, many textbooks have very simple pictures of the ocean circulation or sort of this idea of a conveyor belt overturning. And there's nothing wrong with that. They do represent aspects of the circulation, but they're sort of missing a lot of details. You'll never actually see something as simple as this at any point or any water parts of the arsenals doing the whole circulation over time. There's a lot more mixing. There's a lot more detail. These are just still animations like I showed in those movies. And it's looking at those integrated effects of what's happening with all this variability that then really tells us what's going on, how the small scale physics of the ocean can be integrated. So going to, I guess, the fun premise, people have probably heard about the movie Day After Tomorrow, which suggested changes from the Greenland ice sheet led to a sudden collapse of the ocean circulation in the North Atlantic, stopping a poleward heat transport, and then a new ice age. And I picked a couple of fun little scenes. I'm just going to play a little bit from this.
It's very odd. Boy here registering.
Sorry, 1 second. I think I'm having a technical issue. Right. I'm just gonna 1 second pause. And I'm just gonna switch to the better view of this. Apologies. High floating meeting. No. And I got the wrong. It doesn't seem. No. Apologies for technical issues. I'm going to stop sharing and restart. I must have done something wrong this time. Stop share. And let me try that again. Share sound. And we tested this beforehand and it worked perfectly the last time. Of course, now that it's live, we always have fun technical aspects.
That happens.
Yes. But again, can people see it playing or is it just my screen?
We can see it.
And can you hear the sound?
Yep.
Okay, then, okay. So just a couple of sounds about from the movie.
Boy malfunctioned the other day. I'll put a call in, see if there are any ships near George's Bank to get it.
This boy isn't in George's Bank. He's just off Greenland.
What? What are the odds of two boys failing?
Remote. Make that 3.
And then I want to do one more. Again, related to the North Atlantic current and this circulation in this region.
We've got a lot of work to do, and we don't have much time, so let's get started, please. Vorstein.
All our grid models are worthless.
I don't think grid models are going to be a lot of help here. The Canadians are reporting tremendous circulation moving down from the Arctic. In Siberia, there's a low-pressure system unlike anything we've seen, and Australia just saw the strongest typhoon ever recorded.
Hang on, are you saying that these things are interconnected?
We have to consider the possibility.
The only force strong enough to affect global weather is the sun.
What's NASA have to say?
We've already checked. Solar output is normal.
What about the North Atlantic current?
What about it?
I got a call last night from Professor Rapson at the Headland Center. He thinks the current has changed.
So hopefully that could clear those just two scenes in the movie that talked about, you know, if you, again, when I show this picture to this region, the subpolar North Atlantic, suddenly rapid cooling, and they were talking about the North Atlantic current changing, and then that may affecting heat transport and then cooling coming from the Arctic. So that's sort of the underlying science they were talking about. And the idea they're talking about is the Greenland ice sheet. Suddenly you've got all this fresh water that as it warms, is melting, that's going to impact the ocean, as I'm about to talk about. Now, one thing they really got wrong in that comment, there was that comment about all our grid models are useless. Then someone said, what about your paleo model? Well, actually, paleoclimate models are grid models too. They're the exact same type. We solve the same physics. I have students working on those questions as well as present day. But still, they're looking at equations to look at the physics. But what's relevant and why this came up is Greenland ice sheet. And this plot I like because it really shows the three-dimensional structure. The ice sheet's over 2 kilometers high, 7 meters of sea level equivalent that can be lost, and growing mass loss in recent years has suggested over time the area of the Greenland ice sheet that's melting has been rapidly changing. A lot more melt coming from the ice sheet all around the coastal regions. All the highest melt years with the highest melt are in the recent decades compared to the past. And then that's continuing to the present. The melt is coming from all around the ice sheet. So that means when the water runs off, it's running into the ocean. Some of this heat melting, and you can see melt puddles on the ice sheet, is coming from the warming atmospheric temperature. The air is playing a role. Just warming air is melting the ice. But also, oops, and I should be hiding that. Apologies again. And this is an example from a specific heat wave in 2019 when suddenly there was massive melt, especially in the northern parts of the ice sheet, days of melting leading to lots of water, again, fresh water running into the ocean. But there's also an ocean component. There's about 40% of the increased discharges coming from coastal regions, glaciers that reach the coast and flow into the ocean. And so the ocean also plays a role. Here's an example from some satellite plots off the east coast of Greenland, where they have this fjord. And you can see this glacier with the edge from the difference from the sea ice and the glacial ice in the satellite image, and it slides back. And you can see significant decrease moving back over even a short period of time. And what this seems to be related to is warm ocean water, the ocean currents bringing warm water near the coast. And this section line here is these two plots from the earlier 90s and the later 90s. And you can see sort of more red, just look at the red and the orange, more warm water as changes in the North Atlantic current lead to changes of how much go, say, towards the Arctic versus near Greenland. And then those waters can travel along the coast and mix into the fjords and work to melt Greenland. And here's again from a paper that showed from as we went to the 90s and 2000s, the bottom water, so at the depth on the bottom of the shelf, was very warm. So getting in near the coast of Greenland, and that's important because if you have glaciers that reach the ocean, even if the surface is maybe cold, that warm water can get underneath, can start undercutting, can start melting. And also this warm water sits against the glacier year round. So it's continually melting, not just the summer. So the ocean is also playing, and the change in the ocean circulation are also playing a big role in melting that fresh water, putting into the ocean. So over the last couple of decades, the anomaly of fresh water into the ocean has been massively increases. There was small increase in time, but it's then massively been running in over the last 20 years, pretty much all around Greenland. This plot shows size of these sort of the amount of runoff, and you can really see, for the most part, all the ocean around Greenland are getting more fresh water, both from the surface melt and the melt at depth, the discharge, as well as icebergs. Why do we care? Because fresh water affects the water properties. If you change the fresh water, you're going to change the salinity of the water, the salts. You're diluting it. And if you make salinity is one of the two factors that set the density of the ocean. If you make it more salty or less salty, you make it less dense. That can affect how water mixes into depth. And this is important because Greenland is very close to places in the ocean where we have deep water formation. And to think about that a bit more, let's consider a normal ocean situation, like the Labrador Sea off the coast of Canada in the Atlantic, or the Nordic Seas. If you have cold air coming out of the Arctic in winter, blowing over ocean water, you might have minus 30 air over water that's, say, even 5 degrees. That produces a huge heat flux. It makes it very cold, makes it very dense, but because it's salty enough, that salt stops it from freezing, and the water mixes to deep levels, down up to 1,000, 2,000 meters. But if you add more fresh water, like from Greenland's melt, you start stratifying the upper ocean. You get to this buoyancy cap. And when you cool it, the heat loss becomes smaller, and you start maybe forming ice instead of mixing into deep water, or just having shallow mixing because it's not enough. So that's why Greenland melt from Greenland on can stop all that deep water formation. And then the idea is then if you have some sort of conveyor belt type of circulation, if you have the deep sinking being balanced by the water that's being drawn north and bringing heat, if you're weakening one leg, you're going to potentially weaken the other and weaken the heat go flowing north. Although there's additional factors we need to consider. And especially this Labrador Sea is a very important and interesting region. It's where a lot of this deep sinking occurs. It's very close to Greenland. But the thing I want to bring up now is this melt from Greenland that comes from the ice sheet. So it comes from the coast. And then the deep water is formed in the interior. So we're going to have to look at how the water gets into the interior of the basins. So what's happening in this key region? And as an example, this is from observations. This is just looking at a 20-odd year time series. And you see it gets warm in summer, cold in winter, back and forth. And generally you can see this purple go from the surface down near the bottom. It's suggesting that there is indeed this deep mixing. Water is ventilating from the surface of the ocean into depth. And this is very important because that is part of driving, if you want to say that, deep sinking, the deep circulation that then links into this idea of this conveyor belt. But also it plays a role in taking air-sea gas exchange from the surface and mixing it into the deep water. And think about that, I've got a nice little YouTube video from this large-scale 5-year project to study the Labrador Sea that I led a few years ago.
Breathing brings oxygen into the body. Carbon dioxide is released as you exhale. The ocean also exchanges gases with the atmosphere. The two most important gases exchanged are oxygen and carbon dioxide. There are only a few places in the world's oceans where these gases are inhaled so deeply that they remain for tens, hundreds, sometimes thousands of years. One of these is the Labrador Sea. How does the ocean breathe? Two ways. One is biological. Plankton take up carbon dioxide and produce oxygen. The other is physical. Crashing surface waves push air bubbles many tens of meters down into the sea. In the winter, the breath is deeper. Cold winds draw heat from the surface ocean, making the water denser. The gases from the atmosphere get pulled down with the heavier water deep into the ocean, down to where oxygen is scarce. This is called deep convection. This is the ocean's deep breathing. It does the planet a great service, carrying oxygen to the deepest parts of the ocean to sustain life, and absorbing and capturing CO2. The ocean has taken in about 1/3 of the carbon dioxide emitted by human activity since the Industrial Revolution, helping to slow the rate of climate change. Deep convection in the ocean depends on the interplay of surface temperature and salt concentration in these waters. Just the right conditions are required. As Earth's climate changes, there is increased melting of snow, sea ice, and glaciers. This could cause a thick layer of fresh water to form over the Labrador Sea.
So I'll stop this now, because that's what I was showing with those slides is, why we care about this melt from Greenland and why people have postulated melt from Greenland could shut down this deep sinking, change the heat transport and everything. Now, this has been looked at climate reports and models, but how the AMOC or this overturning circulation is going to vary with climate warming. This bottom axis is the sort of global temperature change. And as you can see, there's a lot of uncertainty. This is one of the most unknown things about how the climate is going to evolve. So how sensitive it is, and it's because of aspects like the melt from Greenland, the sensitive, how much that's going to be, but also how that fresh water gets into the ocean. Because if we look at this in more detail, this is the Labrador Sea. You see, this is a plot of temperature, and you see lots of small scale features. These eddies, ocean weather, like when I showed in that movie, and they transport the waters and that from Greenland, that say the melt into the ocean interior, that may be affecting that deep water formation. And so we need to think about them. And so this is some of the high resolution models we've been running. The plot on the left is basically showing where there's these eddies. We form these features. You see them coming off the coast of Greenland as blue or red blobs. Don't worry about some of the other details, but they're coming in. And then the plot on the right measures how that affects the stratification, how that affects the mixing. And basically where you see the reds and blue colors, the water has got a lot of the fresh water from Greenland. It's very stratified. Even with cooling, it can't mix. It's hard to come down. And so you see it's these eddies are what's bringing this water from Greenland away from the coast. But they're not impacting all of the basin. Other parts are still being able to cool by winter. And these are very small scale processes. You need very high resolution, small grid cells to represent in models. So to understand, even if we know Greenland's melting a lot, but to understand what are those impacts, we need to really look at how the small scale processing computer models are able to represent that so we can look at this. So if we have a high convective resistance from lots of melt from Greenland, you have a strongly stratified water column. But if you take models with different resolutions, say from 1 kilometer, so 1/60th degree or 1 kilometer going down to about 15 kilometers, 1/4, you get very different pictures of this stratification. And in general, as the models are coarser, so they don't represent this exchange, these eddies as well, it's easier for the Greenland meltwater to get into the interior, and you get different behavior in terms of the stratified. So if you can have the eddies, you stratify the Northern Labrador Sea, that actually has sort of less convection initially, so the models are less sensitive to what's being added from Greenland. So you get better predictions of the overturning, and you understand this crucial aspect of these small scale features if we want to then go what's going to happen with these Greenland. And so we've done experiments where we've put in, say, change the amount of Greenland melt, and you can see the amount of that meltwater into the Greenland in the Labrador Sea, and I just got 2 different subregions. You can see it increases with time, but it doesn't increase as fast as it might do in models that don't have all those eddies, don't have all those small scale features. And this is, again, a model simulation that's trying to look at these pathways as we're going along. And depending on what part of Greenland you look, a lot of these waters, some get mixed in the interior by the eddies, but some sort of circle around the Labrador Sea, and then eventually, as this plays, get into the North Atlantic current and sort of circulate around. And so one of the questions we have to ask is, if we know adding fresh water from Greenland is going to have impacts, but might there be lags in the system? Even if it's melting a lot today, might it take 10, 20, 30 or more years before you really start to have significant impacts in the deep water formation? And thus, you're never going to get like that movie that had the movie and having collapses within days. It's nothing like of that level can occur. Again, high resolution models, just look at where these eddies, you can see Greenland water coming off, but most of it, and this is, I just got a small subregion, enters farther south, flows into other parts where it's mixed with saltier water. So again, how we understand the details of where Greenland meltwater gets in the ocean plays a lot of role in determining exactly how, say, the conveyor may be impacted, over what time scales, how strong it may weaken, type of thing. Additionally, recent observations, these are from mooring arrays people have been doing, have pointed out that a lot of that conveyor belt idea is driven by what happens in the eastern basin, less so than the Labrador Sea than we thought in the past, although the Labrador Sea is important for water formation. So again, suggests there's more complexity than just having a simple model. Greenland melts, you put fresh water, you cap the convection, you weaken that conveyor, and that weakens poleward heat transport and cools. There's a lot more going on. So hopefully I've tried to use models and observations and thought to put some thought into this question. The main thing that, looking at being someone who looks at models, we need to consider small scale process into space. So eddies, which are ocean weather, and time, short scale events, storms, ocean equivalent, and how those can integrate together to impact the large scale climate system. And it's something that's really connected. We need to look at how things change in all three if you want to say dimensions or directions. North, south, Arctic, Greenland, Atlantic are tied together, east, west. And I think of that in terms of how do we get the melt that comes from the coast that's flowing in the currents near the coast into the interior that then could affect that up, down, that surface to deep ocean ventilation, the ocean breathing, as that video I showed. So I know I've covered a lot of things probably fairly quickly, and I realize I think there's things I think I could have explained in more detail, but sort of going to the big picture, day after tomorrow, Greenland melt is going to impact the ocean without a doubt. And especially if it keeps continuing to melt, it's going to raise sea level, it's going to affect the ocean, it's going to affect the overturning circulation, but it's never going to completely collapse. There's always some processes that are going to drive mixing. There's wind playing a role there. And so exactly how much it weakens, over what time scale, how that affects, say, heat transport depends on complicated small-scale ocean dynamics. So there's a lot of questions to really narrow down on the uncertainty and hopefully give us better ideas of what are going to be those impacts on circulation, ecosystems, biology, our weather, et cetera, our climate going forward over the next decades. So I guess I will stop here, and I'm happy to answer any questions.
Thank you very much, Paul. That was very interesting. And actually, but I'll come back to that in a minute. It's also quite timely because I'm actually giving a seminar about this at GeoMar. So, but before we start going into any further questions here, let's just briefly talk about what we have next week, in 2 weeks for you. And that's the last episode before the summer break that we have. And there we're going to talk, or we will hear talk by Josean Marquis, who will talk about from the HIFMB in Oldenburg, Helmholtz Institute for Functional Marine Biodiversity at the University of Oldenburg, where we talk about protecting coral reefs in a polluted ocean. So we will hear a little bit about what pollutants can do to coral reefs and how dangerous they potentially are for them, but also maybe some solutions or what can be done to protect these ecosystems and these fascinating structures that you see here. And with that, let me stop this. I want to hand over to my co-hosts here for the first questions.
Yes. Thank you very much, Paul, for the interesting talk. seems that we have at least one person with a little bit of math background in the audience, because the name is also quite fitting. It's Math's Kitten. So the question is, are you using the same grid size everywhere, or are you treating coastal and open sea regions differently?
That is a great technical question. And it depends. Well, depends on which model result we're using, or we're using multiple models. So some of them are, obviously because if you think of the Earth as a sphere, the light allowed to longitude are converging, we have to deal with changes in resolution and that as we go towards the pole, and that we do also explore using higher resolution, say near the coast in the offshore. We do that by nesting one model in another. So there is some of that being done. There's other things I think we could do a bit more. In part, some of the experiments we're trying to put very high resolution everywhere, so we make sure if we just had the coast and then it's going offshore, are we going to lose some of that fidelity? So I know that's just maybe a bit long-winded answer, but yes and no.
That's always the best question. It's
yes.
Or the best answers, the it depends questions. Yeah, thank you very much.
Awesome. So maybe for those who are still a bit shy, to help set the stage for everyone further, I can pose another question. Could you explain a bit maybe what deep water formation is for those who kind of not familiar, and why it plays such an important role in regulating Earth's climate?
Sure. So if you think about the ocean is about, on average, about 4 kilometers deep. Obviously, it varies from coast towards where it's shallower to the deep ocean in the interior. And for any fluid, you want to have lighter water over denser water, that sort of stratified like that. So typically you'll have warm and fresh water near the surface, colder and saltier water down near the bottom. And deep water formation is the process where water can go from the surface to the deeper ocean. So it actually allows you to exchange properties. This only happens in sort of subpolar regions, because that's the only place that's cold enough to suck enough heat out of the ocean in winter to make it cold and dense enough to sink to the bottom, which is also why all the deep waters are cold. If you go to the equator and look at the deep ocean, it's 4 degrees Celsius, even if the surface water is 28, which tells you that you're not forming water, because the equator's obviously got the sun shining on it, it's warm. So it's only at the high latitudes where the water forms, and it sinks and flows through the deep ocean. That's also why deep waters formation is important, because it's only a few places that allow the waters to go down and then travel around the rest of the world. And it's when the ocean's in contact with the surface that it can exchange gases like oxygen and CO2. So it's only in those deep water formation places that those gases get transported to the deep ocean. Oxygen transport's, of course, very important for marine life. You need oxygen so it can breathe and etc. And CO2, if the atmosphere's got an increased CO2 concentration and it gets absorbed by the ocean and then mixed down, it's being sequestered, at least for a period of time. Once that CO2 is in the deep ocean, it can't be remixed to the atmosphere versus at least near to the surface. So the deep ocean circulation plays a role in delaying, if you want to say, the CO2 increase in the atmosphere. It puts the water in the deep ocean for decades to hundreds of years, and that's that period of time before it gets back to the surface can be re-released and increase in the atmospheric concentration. Again, there's more complexities, but so deep water formation is basically the window of how the deep surface can evolve, how the deep circulation is driven. So if you can't have those connections, the deep circulation is either going to potentially slow, it's going to start mixing the CO2 as upwards, eventually going to slowly lose oxygen, which are all going to have detrimental effects.
Thank you very much. Yeah, actually, I wanted to ask a question for myself, but we just got something from the chat, so I'll do that instead. There's a thanks from the chat for the presentation, where Bärbel I think, I don't know how you pronounce that, is asking, I'm wondering how much of your data, if any, comes from the Argo floats, and how that might be affected by potential cuts to the nowhere in the US. So that's a very specific question. Maybe you can also explain a little bit what that means in terms of what Argo is and so on.
Sure.
I know it, you know it, but maybe the audience doesn't necessarily know it.
Yeah, that's great. So, historically, measurements in the ocean were taken by ships. Research ships would sail out, go along and lower instruments in the ocean to make measurements. Satellites can take pictures of the ocean surface, but in general, the ocean is opaque to satellites. They can only measure a very thin layer at the surface of the ocean. So if we want to get data in the interior of the ocean, we need to have instruments in the ocean. So typically from ships, where ships were sailing. So there's expense, there's all sorts of aspects, and generally it's difficult to get data from, especially the deep ocean. The ship would have to sail to a point, lower the instruments, make measurements. So data was also concentrated where a lot of the ships went. So Northern Atlantic had lots, off around Antarctica, parts of the Arctic didn't, as an example, in the South Pacific. So people wanted to make measurement. So they developed these robotic floats. They're, I guess, even you could call them a type of drone, although they're not really controlled, that are in the ocean. They put in the ocean, they float, and just by changing their, having a bladder that goes in or out, sort of changing their internal volume, that changes their density, and every 5-10 days they do a profile of the ocean, up and down, making measurements. And there's 3,000-4,000 of them now in the world's ocean, continually observing. Since that started in the early 2000s, we have an order of magnitude more data in the ocean than we used to have. There's still some issues like in ice-covered regions like the Arctic, because sea ice impacts when they come to the surface and want to send it by satellite. So they're collecting data. Now, we're doing modeling, so the model is solving the physical equations. But that Argo data is what we use to evaluate the model and say, does it make sense? Is it working? Is it answering the right questions? As well as other data. So that data is crucial for studying the ocean, asking questions, etc. Now, this array, as I said, there's about 3,000 floats, 4,000 floats in the ocean. They, on typical, last about 5 years, so they're being replenished by time. And the US pays for about half of them. Canada's 10%, EU is about 30%, and there's other countries doing that. So that is a worry that if NOAA is dropping with all the US budget cuts, what is going to happen to that array, which we depend on, is really important for ocean forecasting as well as the more theoretical modeling I'm doing. And so the question is, will other countries step up and spend the money if the US doesn't for at least the next 3-4 years, hopefully only that, etc. So yes, there's definitely concerns. It's not going to affect our modeling short term, but it's going to affect everyone incrementally if that was to continue.
Thank you, Paul. Yeah, we have the worries as well that this someone has to fill the gap, basically, right? Just to clarify this, we have your chat here, and I thought it was Bärbel, and then WHI was her surname, but it's just W, and then there was a hi to you. So it's two different things. But anyway, that happens. I'll forward, give back to my colleagues to ask the next question now.
I mean, it happens to the best of us. So next question is, you mentioned these high resolution computer models in your presentation. I'm not sure if everyone is so familiar with these kind of models as the two people who are already asking questions seem to be. So maybe you can explain for those of us less familiar with modeling, what makes these new models so important for understanding Arctic change today compared to earlier ones?
Great question, and I probably went over that much too quickly. So the models are solving equations that represent the physics of the ocean, the thermodynamics, the process of the sea ice, etc. And as I try to say, because we can't solve for every molecule of the ocean. So I remember someone estimating there's 10 to 26 molecules of water in the ocean. Even the best supercomputer today couldn't come even close to trying to simulate that. So we have to break it into pieces or chunks, these discrete chunks, so like a grid. And depending on how long to run the model, how you want to do it, you have different sizes for the grid. So typically a climate model that has many, many elements of the climate system that wants to be run century has to have grid cells that are bigger, tens or even multiple tens of kilometers per size. So you're averaging the ocean properties within them, which if you're looking at the Earth as a whole is still fine. But if you want to look at details like how things go from a fjord where Greenland has an ice sheet to a coast, to an eddy, to the interior, you need, that gets harder in those models, which is why there's aspects of that uncertainty. So now modern day computers allow us to put much, for this, put much finer resolution, so we can represent much smaller scale processes that on their own might be small, but if they integrated effect of putting them all together, could still affect the large scale circulation. So in one sense, the background ideas of the models are similar. It's just you're able to represent a lot more of what's going on in the ocean than than was before. I guess there's a case. Think about you are trying to say, something non-scientific. You're going for a hike in the forest or in the mountains or whatever, and you need to go to the points. And if you've been told you've got points A, B, C, and D to look at, you can walk, you can sort of say, okay, I know the elevation, know where I'm ending, but you don't know are you going to go up and down? Are there climbing over a pass down, or is it just flat? Are you going to have to meander around a river? Versus now, if you have lots of little details, you'll know exactly what you're doing. In the hiking case, that's just okay, planning your day. But for a model, again, it's for the ocean. It's still looking at all those other features that are actually there and that may be affecting the solution, and allowing us to get closer to the observations like those collected from the Argo floats and other processes.
Yes, thanks a lot. Super interesting. I was already nerding out a little bit in the background and thinking about how the grid cells look in your model, if it's always the rectangular ones or if you're also using like triangular ones or different kinds. But maybe that's a question that we can answer after the talk. I think we can move on with the next question.
Sure. You already touched on the connection between the Greenland ice sheet and the ocean conveyor belt, but for those, who wants to know what's next, maybe building on that, can we pose the question like how close are we to seeing measurable changes in the ocean conveyor belt due to Greenland meltwater maybe? Because so there is also another maybe connection to this. So what will be the early signs scientists are watching for maybe?
Again, that's a great question. One of the harder points is how far back you can go. So can you look at changes and what are the changes? People can try to go back with paleoclimate records, like look at sediments like tree rings. People look at on land for knowing what past conditions. You can look at ocean sediments, look at some of the shells of marine life in the past to try to get ideas about conditions. And then as we go more recently, we have observations. But one of the problems historically is ships would go out and maybe make one measurement every year, etc. And there's a lot of higher frequency variability, like the weather, the noise, as I try to show in some of those animations. And people have looked at, now that people have put arrays where they actually leave moorings in the ocean full time over a number of years trying to observe this, there's a lot of high frequency variability. And if you just sample it, say a ship cruise here, 1-2 years later, is the difference just you're getting into some of the noise, or are you getting into the actual big picture change? And that's another concern. There's an array in to study this overturning the Atlantic that I'm worried is not going to get funded again because it's mainly US funded going forward. But so we do need to be looking at, we need to look at, how is the salinity, say, in the interior of the Labrador Sea, parts around the North Atlantic, the Argo floats are happening, some of these arrays. Yeah, we need to, measurements of the ocean, and can we see significant changes over a number of years? So there's definitely people doing a lot of studies to try to figure out what are the key indicators, and then how do we see those changes? The hard part is there's a lot of variability, integrated effects. When it's going to happen, that, like I said at the end, that's where I don't think we have a good idea. Something is, if Greenland keeps melting, there's so much fresh water, it's got to have an effect. But is it going to be 10 years? Or is it going to be 50? I don't think, I could give a number, but I don't have confidence in that. So, that's what I would say is yes, there's going to be effects. They're probably going to be very significant, but where they're going to happen is where we really still have a lot to figure out.
We also have another question from our chat. I'm already apologizing because I probably will mispronounce the name, from Archiflip. There are many brine pools on the bottom of the ocean. How does the ocean desalinize? Sorry.
So, so the ocean has its salinity, which is the salts. They come from biogeochemical cycles, long-term erosion, dust deposition on very long time scales. And there's places they can be concentrated. For example, we have hydrothermal vents in the deep ocean, or places near the coast where you get a lot of evaporation, produces salts, and you get very high brine pools. You also get brine pools when you form ice, because as you freeze seawater, you squeeze some of the salts out, putting that in the water underneath. Because sea ice is not fresh, unlike glacial ice, which comes from precipitation on land and slow accumulation. But those processes can be slower than if you're melting. If you're melting enough of Greenland, or just say permafrost on land or land glaciers, you're putting a huge amount of fresh water in. And that can dilute the ocean in some places quite quickly. So generally, if I didn't have put a figure in, the tropical oceans are getting saltier because you've got more evaporation, warmer climate, if you want to say an enhanced hydrological cycle, but more precipitation plus the runoff at higher latitudes. You're also getting big gradients. So it's not that you're not getting one or the other, it's just where they're being localized and enhanced is changing, and it will likely continue.
Thank you very much. We have a couple of remarks here. One I already answered about that ice melt does not change sea level rise, but well, it depends where the ice comes from, right? So
it depends if it's sea ice doesn't, because sea ice is floating in the ocean already, and that's not going to have an impact. But land ice is what can raise sea level, because that's actually adding liquid and mass into the ocean.
Yeah, so I think that's what the clarification here needed, but I already put that in the chat. I hope. Otherwise, if you're still unsure, then put it down in the comment section, basically. I'll ask my last question, unless there is something I see. Nothing right now. There is a remark, but that goes to Fake Flip, to the question about the salt brines before. So I'm not quite sure if this is related, this is addressed to you. But let me ask from my perspective. Since I mentioned that currently in one seminar we actually talk about with students in the study program about exactly what is going to happen to the AMOC and to the overturning and all of that is basically being picked up by the Day After Tomorrow movie. How do you actually in the University of Alberta, how do you address this uncertainty where if it would break down, it would have large consequences, not as bad as in the movie, but it would still have large consequences. But we don't know yet, right? So there is still, as you said, a lot of uncertainty. So how do you deal with that? How do you teach that, or how do you discuss that in classes and so on?
That's a great question, because, for example, I teach as sort of an undergraduate course, a large course on the oceans, generally to non-specialists, to people in any area of science, arts, etc., who want to know something about the ocean. And so I have all sorts of lectures on that. And towards the end, I have a lecture which I titled The Day After Tomorrow. I start with some of the same scenes and everything, and then start getting the science. And same thing with, linking to the overturning. And, I find this is something, it's a challenging thing, because I show the picture of the conveyor belt, and then I say, here's why we do it, and I explain it, and here's the strength of having this really simple model that has just connections, that if you have a conveyor and if one part changes or slows, that's eventually going to affect everything. And then I say, but it's got all sorts of things wrong with it, or limitations, because water parcels aren't doing everything. There's lateral exchanges as well as north-south. There's mixing, there's eddies. And a lot of students find, wait a second, you just said this model was good, and now you're saying it's bad, or it's got limitations. And it's something one has to really think about. But I guess, how well I do it it probably depends upon the students and everyone. We all are getting this, but I think it's important to really make clear there's advantages to simple models, but there's always limitations. Don't just assume, you can always get it. You have to look at all the different pieces. And in terms of uncertainty, again, that's a challenge. I think that's something I'm going to say, we try. I think this is something as scientists, events like this is a great outreach, is something we don't do well enough in terms of computing science, computing that uncertainty or how that we don't understand everything, or some people take that as means we don't know anything, but that's not the case. And so this is something, as I think ocean, marine, climate scientists, we all need to explore how better to do that, because it's a challenging topic. People like their black and white versus a spectrum and probabilities and things. So like I said, I explore trying to talk about what it does explain, what it doesn't, what that may mean. Am I doing it the best? Probably not. It's just continually, I think we all need to talk about and reinforce.
Yes, thank you very much. I think that's exactly what scientists basically need to do, right? They need to convey the uncertainties, but that uncertainty doesn't mean you don't know anything. Knowing uncertainties is actually knowing a lot in the end, right?
Yeah.
Knowing about the bounds of uncertainties and so on. Just maybe one last, because we got another remark from one of the questions in the chat from Bushman. Regarding the glaciers, because I wrote in the chat that glacier ice or ice caps can actually lead to sea level rise, and then the question was, is that actually a significant amount of mass that can come from that? And I think you can basically just say yes, right?
Yes. Someone has estimated if you melt all of Greenland, there's 7 meters of sea level potential there. Antarctica has about 50 something, so you could raise sea level a lot. And as I say that, brings me to another movie I use for teaching, something called Waterworld, that talks about the global warming, the ice caps melt, and then suddenly there's no land, and everyone has to live on the water and everything, And as a thought experiment, I asked students in classes, let's just see how big the ice sheets are. And yeah, you can raise sea level about 60 meters, which would be significant. It probably wouldn't be great for Bremerhaven, and then the North German coast, versus I'm in a city that's at a base elevation of like 800-900 meters, but yeah, and again, not everything's going to melt, but yeah, there's a lot of sea level potential in the glaciers, and how that feedbacks. That's again one of the big, I think, open questions. Will you have rapid collapse of parts of ice shelves, including Antarctica?
Thank you very, very much. I think that was a very good last remark. And with that, I thank all our viewers. I obviously thank you, Paul, for taking the time also from the far distance to talk to us today. And I hope you join us in 2 weeks, for the last episode before the summer break. And with that, I would like to give you our jingle again, and then I say goodbye, or we say goodbye. Oh, no, it doesn't start. That's a problem. Okay. 1 second.
Wohnzimmer ist Wissen her.